Every day, we tap, swipe, and scroll on touch screens using our phones and tablets. We expect the screen to respond accurately, remain smooth, and resist scratches even after long-term use. This performance is made possible by thin film technology, where extremely thin layers of material are deposited on the surface of the screen to give it special electrical and optical properties. Thin film technology refers to the process of depositing very thin layers of material, typically ranging from a few nanometers to several micrometers, onto a solid surface called a substrate. These thin films allow us to modify surface properties without changing the bulk material. Because of this, thin films are widely used in electronics, optics, energy devices, and sensor applications. Thin films are important because they can conduct electricity, control light transmission, protect surfaces from wear, and improve chemical stability. To fabricate these thin films, controlled deposition techniques are required. In this video, I will focus on sputtering, which is a PVD technique. Sputtering is a physical vapor deposition process used to deposit thin films onto a substrate. In sputtering, atoms are removed from a solid material known as the target by bombardment with high-energy ions. These atoms then travel through a vacuum and deposit onto the substrate to form a thin film. The basic principle of sputtering is based on momentum transfer. When energetic ions collide with the target surface, their kinetic energy is transferred to the target atoms. If the transferred energy exceeds the binding energy of the surface atoms, those atoms are ejected from the target. The sputtering process begins by evacuating air from the chamber using a vacuum pump. Creating an ultra-high vacuum environment is important because it prevents contamination and allows sputtered atoms to travel directly from the target to the substrate without interference from air molecules. After vacuum is achieved, argon gas is introduced into the chamber. Argon is used because it is chemically inert and relatively heavy, making it effective for transferring momentum during ion bombardment, while not reacting with the target material. A high voltage is applied between the target and the substrate. The target is connected as the cathode, which is negatively charged, while the substrate is connected as the anode. This electric field accelerates charged particles inside the chamber. Electrons emitted from the target collide with argon atoms and ionize them. This process creates plasma, which is an ionized gas consisting of free electrons and positively charged argon ions. Plasma is essential for sustaining continuous sputtering. The positively charged argon ions are attracted to the negatively charged target. As they accelerate toward the target, they gain high kinetic energy and strike the target surface, causing ion bombardment. During ion bombardment, energy is transferred from the argon ions to the target atoms. If the energy is sufficient, surface atoms are ejected from the target. These ejected atoms, known as adatoms, travel through the vacuum toward the substrate. When the adatoms reach the substrate surface, they lose energy and condense. Over time, continuous depositions result in the formation of a uniform thin film with controlled thickness and composition. There are three main types of sputtering techniques used in thin film deposition: direct current sputtering, radio frequency sputtering, and magnetron sputtering. DC sputtering uses a constant direct current voltage applied to the target. It is simple and inexpensive but can only be used for conductive materials. RF sputtering uses an alternating voltage, typically at 13.56 MHz. This alternating field prevents charge accumulation on insulating targets, allowing both conductive and insulating materials to be sputtered effectively. Magnetron sputtering uses an additional magnetic field near the target. The magnetic field traps electrons close to the target surface, increasing ionization efficiency. This leads to higher deposition rates and reduced substrate heating. Sputtering offers several advantages, including low deposition temperature, strong film adhesion, high uniformity, and precise control over film composition. These advantages make sputtering suitable for advanced thin film applications. In touch screen device, sputtering is used to deposit transparent conductive thin films. These films allow electrical signals to be detected when the screen is touched, while still maintaining optical transparency. Besides touch screens, sputtering is widely used in semiconductor fabrication, optical coatings, sensors, and thin film solar cells. Its versatility makes it one of the most important deposition techniques in modern engineering. In conclusion, thin film technology plays a vital role in modern science and engineering. Sputtering is a key physical vapor deposition technique that enables precise, high-quality thin film fabrication for a wide range of applications.